In this lesson, we'll cover functions and their graphs. So to start with, a function is an equation. So an equation is something like y equals 2x plus 1, but it has this condition that says every input, the x value, goes to exactly one output, the y value. So let's ask the question, is the equation y equals 2x plus 1 also a function? And in doing so, we're actually going to graph it. To graph this thing, I'm going to set up a table of values, and I'll choose some numbers for x and find their corresponding y values. So I think I'll choose -2, -1, 0, 1, and 2. All right, this equation here, if I put -2 in place of x, I'm going to solve for the corresponding y value and then plot this point. Let's see what happens. So when x is equal to -2, I take this input and I put it into my equation. Let's see, 2 times -2 is -4. And if I add 1 to -4, I get -3. Here we took one input and it went to exactly one output. So far this looks like it might be a function. One input goes to one output. If we graph this point, that was x is equal to -2 goes to y is equal -3. So not only can I see it on the table of values, one input going to one output, I can see it on the graph as well. You go to one x value, an input, and you only get one output for a y value. There's never another one above it or below it. So let's actually complete this table. So going through it just maybe a little more quickly here. If x is equal to -1, y is going to be, well, that's 2 times -1 plus 1. That's -2 plus 1. That's -1. Again, here we had one input, one x value, that went to one y value. And if you look at that on your graph, you get this spot right here. You go to the input of -1, and you get exactly one y value, also -1. There is never another one above it or below it. Okay, check x is equal to 0. Let's see, that is y is equal to 2 times 0 plus 1. That's 0 plus 1, which is 1. So here at the input of 0, you get the output of 1, and there's never another one above it or below it. Continuing, okay, for x is equal to 1, y is equal to 2 times 1 plus 1, which is 3. Again, we're just getting one output, so that was 1, 3. And then one more. When x is equal to 2, y is equal to 2 times 2 plus 1. That's 4 plus 1, which is 5. So again, at 2, we get 5 and 5 only, and that's it. And I think this is enough to get the entire graph of this equation. It's going to be a line going between those points. So I'm going to draw it in like this, and that's it. So to answer the question, is this thing a function? The answer is, yeah, it is. The reason is, first, it's an equation, but also every x value that you choose, the input, goes to exactly one output for y. There's never like a second or a third one. And the way that shows up on the graph is, if you choose something in the domain that's an input, and you look at the corresponding y value, you get one, and you don't ever get a second one. There's never another one above it or below it. So how do you tell if an equation is or is not a function? A simple way to do this is by using the graph of the equation. So here, I don't actually have the formulas for them, like you don't see the equation, but we do see their graphs. So we have this one over here in red and this one in blue. One is a function and one is not. So which is which? If you look at this graph over here and you're trying to decide if it is or is not a function, what you can do is look at an input, an x value on the x-axis, and ask yourself, how many outputs are there? How many y values do you get? So like for this spot here, I see there's one spot here and there's never another one. Does that happen for every single x value, each input? And the answer is yeah. Like here at 0, the input, you get one y value, but you never get a second one. Over here, same thing happens. You get exactly one output, one y value, and you never get another one. There's this thing called the vertical line test, where if you draw a vertical line and it only goes through the graph once, and this happens every time on your graph, it means that it is a function. So I'll say, this is a function. Because every vertical line that you draw, no matter where it is, will only ever go through the graph at most once. And we call this thing the vertical line test. So looking over here, is this a function? And it looks like the answer is no. Like, what goes wrong? If you choose, let's say, maybe this input, how many outputs are there? There's two. There's one here, and there's one here. So I know that this thing is not a function. So this is not a function. The way to use the vertical line test would be to find one vertical line, just one, that goes through the graph more than once. And there's a lot, but I'll choose this one here. So here we go. Here's a vertical line. It goes through this spot and this spot. And that is it. Once you find it, I know that this thing is not a function. In example 2, we're going to evaluate a given function. And we'll get some practice using function notation. So here I have f of x is equal to 5x minus 4. This is the same thing as writing y is equal to 5x minus 4, in that y and the symbol f of x are interchangeable. So this thing here is called function notation f of x. That's how it's read. You'd say f of x. So this is a notation only. It just tries to indicate, okay, we have a formula that takes an x value to a given y value. Let's try it out here. So for this equation, this function, what is f of 100? What this symbol means is you're choosing 100 for your x value, your input, and you're asking, well, what does the function do to that number? To figure that out using this formula, you put 100 in place of x. So it would look like this. You'd write down 5, open up a set of parentheses and put in the input, and subtract 4. So this is what f of 100 means. To simplify it, that's 500 minus 4. And altogether, this means that f of 100 is equal to 496. So in this notation, you're saying you're choosing 100 for x, and you got 496 for y. Let's try it again. Here is f of negative 1. What's that equal to? Using this function notation, f of negative 1 means take the formula, put negative 1 in place of x, and then simplify it. So that's 5 times negative 1. So that's negative 5 minus 4, which is negative 9. What this means altogether is f of negative 1 is equal to negative 9. The input of negative 1 goes to the output of negative 9. So in parts A and B, I just chose numbers, put them into the function, and we got numbers back. But you can also put in expressions with variables into the function as well. It doesn't just have to be numbers. So like, what is f of x plus 1? Again, we're not saying we're multiplying f to x or 1. This is a notation which is saying what happens if you substitute x plus 1 in place of this x. Let's see. Okay, this notation means you take your function, and wherever you see an x, you're replacing it with x plus 1. So if I want to simplify this, I guess I'll have to distribute. I'm going to multiply the 5 into the parentheses. When I do, I get 5x plus 5, and then we have this minus 4. And if we combine like terms, we get 5x plus 1. So this is what f of x plus 1 is equal to. F of x plus 1 is 5x plus 1. So it actually turns out that it's another equation. And likewise, here we have f of 2x. Same thing. To figure out what this is equal to, you go to your equation, and wherever you see an x, you're replacing it with 2x. To simplify this, 5 times 2x is 10x. There are no more like terms to be found. So f of 2x is equal to 10x minus 4. It doesn't matter how complicated your formula or your function gets, the process is the same. Wherever you see an x value, you replace it with like 100, -1, or maybe some expressions that depend on a variable. And in this last example, example 3, we're going to use the graph of this function to figure out what these things are equal to. And at the top here, I have a few definitions that I wrote down. To start with, I'm calling this thing a function, and is it? It looks like it. Using the vertical line test, any vertical line that you draw will only go through the graph once. All right, with that out of the way, part A asks for h of -5. What is that equal to? Okay, this means you're inputting -5 into your function, and you want to figure out what the corresponding y value is. So here the input is x equals -5. The output is -2. So h of -5 is equal to -2. And that's read directly from the graph, no computations. Likewise, what is h of 1? This is saying you're inputting 1, and we want to know what the corresponding y value is, and that's 4. So parts A and B are found just by figuring out y values on a graph. For C and D, here we're looking for an x-intercept and a y-intercept. Now, an x-intercept is any point on the graph that falls on the x-axis. So starting with that, here's the x-axis, and I see the graph actually equals the x-axis right here. So this spot is what we call an x-intercept. So what are the coordinates of this point? It looks like the coordinates are -3 for x and 0 for y. And if I look to the left and to the right, I don't see any other time that the graph crosses over the x-axis, so this is the only one. So there's just one x-intercept. Likewise, a y-intercept is a point that falls on the y-axis. And I can see there's one here. In fact, this is the only one. And this appears to be the point 0 for x and 3 for y. One thing to point out about an x-intercept is that the y value is always 0. If you're on the x-axis, that means you aren't up or down at all, so that's indicated by putting a 0 in place of y. Likewise, a y-intercept will always have an x value of 0, because if you're on the y-axis, it means you're not right or to the left, and that's indicated by putting a 0 in place of x. For the last two parts, for domain and range, the domain is the set of all x values on your graph, and the range is the set of all y values. So what is the domain of this function? So you have to know where the graph starts on the x-axis and then where it ends. So like over here, I'm looking at the graph, and here, if you go a little past -5, maybe to -6, if you look up or down, there are no y values there. So that means -6 is not in the domain of the function because there's no graph above or below it. The first time you actually get a point on the graph is when you're at -5. This means that -5 is in the domain of your function because you get this corresponding y value. In fact, from -5 all the way to +6, there's always a graph either above or below the x-axis. So if you want to know what the domain is, which I'll label as D for domain, it is this interval. It's all of the numbers from -5 up to and including +6. This closed circle and this closed circle mean you're actually including the point, but you get everything in between those values and nothing on the outsides, and that's why this is our domain. Now, what about the range? What is that equal to? So I'll use a capital R to represent the range, but this is the y values. What are all the y values that you get back for your function? So it's analogous to figuring out domain, but you look at the y-axis and you ask, how high and how low is the graph? It looks like the lowest y value is here at -2. The second you go lower than -2 and you look to the left and to the right, the graph doesn't exist there. So this is your starting point. You get y values as you move up the y-axis. You look to the left, you get a y value. You look to the right, you get a y value. And it looks like we're stopping here, which is at 4. The second you go past 4, there's no graph. So this is the range. It's everything from -2 up to and including +4. So that's from -2 to 4. Now you get a bunch of repeated values here at 4, like there's, well, infinitely many x values that it corresponds to, but that's fine. As long as you get at least one, you include that value in the range. And that's it for this example.